Gravity, the force that keeps us grounded and planets in motion, has puzzled scientists for a long time, especially when it comes to understanding its behavior at the tiniest levels of particles. This quest for a theory of quantum gravity has been ongoing for nearly a century. The aim is to have a single set of rules that govern how gravity works for everything in the universe, from galaxies to subatomic particles. The heart of this challenge lies in a clash between two major theories: Albert Einstein's theory of general relativity and the principles of quantum mechanics. Einstein's theory replaced the simple attraction concept of Isaac Newton with a revolutionary idea. It described how matter and energy bend space and time, causing objects to follow curved paths. In other words, gravity is not a force but the shape of space itself. General relativity has successfully passed numerous tests, but it's expected to have limitations because the universe isn't entirely smooth. Planets, stars, and everything we see are made up of atoms, which consist of even smaller particles like electrons and quarks. These particles interact by exchanging other particles, creating forces of attraction and repulsion. Among the four fundamental forces in the universe, only gravity lacks a quantum description. This means we don't precisely know how gravitational fields come into existence or how individual particles behave within them. The problem is that while gravity appears as a force in our daily lives, general relativity suggests it's more than that. It's the curvature of space. This is quite different from how other quantum theories treat space as a flat backdrop for particle behavior. The trouble begins when trying to calculate how space curves around tiny particles like electrons. To tackle the complexities of quantum mechanics, physicists developed a technique called renormalization, which helps simplify the math. However, when trying to apply renormalization to gravity particles, called gravitons, the situation becomes exceedingly complicated. Gravitons introduce more curvature to space, leading to a cascade of mathematical challenges. It becomes impossible to perform realistic experiments to determine anything, leading to an halt in understanding gravity at the quantum level. Given that detecting gravitons directly is immensely challenging, scientists are exploring alternative approaches. Two prominent theories are loop quantum gravity and string theory. Loop quantum gravity suggests breaking up space and time into tiny bits, resolving the conflict between particles and space-time. String theory, on the other hand, replaces particle with string-like entities, where gravity naturally emerges from the mathematics. I have already made a dedicated video on string theory, so you can check that out. String theory also hints that space itself may not be fundamental but an emergent property of particle interactions. This suggests that gravity and space may be more interconnected than previously thought. In a way, space could be an emergent phenomena resulting from the interactions of smaller particles, similar to how temperature emerges from the average speed of air molecules. While these theories show promise, they are far from complete and many mathematical challenges remain. Physicists are still working to achieve an accurate description of quantum gravity. They hope that astrophysical observations, especially from gravitational wave detectors, may provide clues to guide them in the right direction. In conclusion, understanding gravity at the quantum level is a profound challenge, but scientists continue to explore innovative theories and rely on future experiments to uncover the mysteries of this fundamental force in the universe.